Here we are in Desmos, and let's take a look at a function. Y equals cosine of x. This looks like we've seen many times before. The cosine function, we know this is a solution if we have a mass on a spring. This is a function we use all the time, but have you ever wondered how your calculator calculates it? We're going to see that there's another way to write cosine that is more calculatable. Probably you would guess that a polynomial is a simpler thing to deal with than cosine. What if I told you that there's a polynomial that's equal to cosine? Well, that's not exactly true, but it's almost true. Let's take a look. So where could I start? I know that the value of this function cosine at x equals 0 is 1. So that's probably a good place to start. So I can say this function, this polynomial I want, is going to start with 1. But what happens now? It curves downward. Do you know a function that curves downward with this kind of shape? Well, when I think of polynomials and curving downward, the first thing that I think of is a parabola. So what if we said minus x squared? Why is it minus x squared? Well, it's a frown, not a smile in this region. So I see that curved too much. So I need to subtract not quite so much x squared. What if I said x squared over 2? Well, that looks a lot better. How about x squared over 3? That's not enough curve. So let's stick with the x squared over 2. But now I see that the function is doing pretty well for a while, but it needs to bend back up. We need this handlebar mustache to happen. No, not that much. What can we add? Well, we know we need to add something to curve it back up. And this is also an even function. What does that mean? That means if I drew this with ink on a sheet of paper and folded the paper in half along this line, that I would get a print of the other half of the function. So it's a mirror image function. We call that an even function. So I can only use even functions here to add up to the function that I want. So far we have this. So what's the next even option in a polynomial? Well, it would be x to the 4th. Clearly that's way too much x to the 4th. We were doing so well. Maybe we need to divide by, we divided by 2 before. What if we divide by 4? That is still not enough division. I'm adding too much x to the 4th. Well, let's see where we can go with this. Maybe that's better. Better still. This looks like we're matching with just 3 terms in a polynomial. We're matching cosine all the way from negative pi over 2 to pi over 2, just about. That looks pretty good to me, but what about these guys? Can we do better? Well, let's see if we can continue this trend. The next thing I know, I need to bring the function back down. Look, it's going way too high here, so we need to subtract something. And it needs to be an even function, so let's see what we can do. I'm going to subtract, what's the next even polynomial term I could use? X to the 6th. We've clearly subtracted way too much. Could it be divided by 5? That's not enough. 6? How about 6 times 5? Look at that. Now we're matching almost from negative pi to pi. Just a little gap here on each side. Can we do better still? Let's check it out. I think we see a pattern here. It looks like if I add x to the 8th divided by, what do we call this thing? Where we multiply numbers down to 1, factorial. Desmos knows this. Now I've got a whole period of convergence here from negative pi to pi. Looks pretty darn good. Let's toggle that. Looks like a good fit. Can we do better still? Better still? Let's see if we can make a way to add these terms one at a time. Can we use sigma notation to sum some terms? Well, I know that what I'm seeing in this function is a sum of terms. Desmos, you can type sum. We're going to start at 0 and go up to some final term, capital N. So what do we first observe? Positive, negative, positive, negative, positive, negative. Do you know something you can multiply by itself that goes positive, negative? If you're thinking -1, we're thinking the same thing. -1 to the n. Let's add some more to this. I know that I need to have polynomial powers, and they need to be even powers, so I'm going to say to the 2n. And we're dividing by that same power, 2n factorial. Let's add a slider for n. We'll get rid of our purple function here. Here's the parabola that we had to check our fit. And let's change this slider. I'm going to change the slider from 0, let's say 1. We'll start at 0, up to 20 in steps of 1. Now what will happen if we add one more term? Each time we add a term, we're getting better fit. So at 9 terms, I'm seeing almost no difference between the two functions here. What if I zoom out? Oh, there's the failure. What if I add more terms? I can do better. So if I'm willing to add more and more terms, I can fit more and more of my cosine function. So is there a polynomial that's equal to cosine? The answer is not exactly. There is something like a polynomial, but it has infinitely many terms. And part of the definition of polynomials is that they have finitely many terms. Let's watch this thing converge. We're going to use this bouncing slider. Here we go from the linear. Let's slow it down. This is many periods of cosine that we're fitting with a polynomial. And look, when it fails really badly. But when it converges really well. This is a property of this tool that we're using, this series, which is called Taylor series. We'll explain why they work in the next video.